3 of Hello class, welcome to week 3 of Calculus VC. Today we're going to do a quick review of all the integrals according to what we see in unit 6 here, topic 6.8, finding antiderivatives and indefinite integrals, basic rules and notation. So far in Calculus AB, we've learned how to take the integral of a function, and let's suppose I want to take the integral of this function f prime of x dx, and of course this is going to be an indefinite integral. This will just equal f of x, and we will always include plus c. So what we will start off with this class is going through the list of integrals starting with a constant. So let's take the integral of 1 dx. This result will be x plus c. The integral of 2 dx is going to be 2x plus c. The integral of e as a function itself with no exponent whatsoever would just be e times x plus c. The integral of pi dx will also be pi x plus c. Now, what we can expect from all these sort of functions is that these are constants. There's no x that is multiplied to it. To see the next category of functions, suppose we have the integral of a constant a times x dx, where x is just to the first power. We know that the result of this would be a x squared over 2 plus c. And the general formula for this would be a times x to the n, the integral of this function, should be equal to a divided by n plus 1 times x to the n plus 1 plus c. So let's take a look at a couple of these examples. For example, the integral of 3x cubed dx. We could always imagine this as a function in which a constant multiplied to a function, the constant can always come out. So here we have 3 times the integral of x cubed dx. And what that allows us to do is to then go with this integral formula in which we would add 1 to the exponent. We would then divide by that same exponent, and we still have this 3 left over. And I'll include everything inside the brackets as what was provided for the integral, so that this becomes 3/4 x to the 4th power plus c. We see other sorts of functions that still follow this rule, a times x to the n power. When we take the integral of this, we could always take out the constant a, so we have x to the n power dx, and this is going to be a times 1 over n plus 1 times x to the n plus 1 power plus c. And so for example, let's say we have x cubed, the integral of this. Let's suppose that we wanted x to the 5th power with the 3 coefficient in front. The first one will be 1/4 x to the 4th power plus c. The second one will be 3 over 6 x to the 6th power plus c, but this is simplified to 1/2 x to the 6th power plus c. We can also treat radicals. So for example, radical x, the integral of that would just be the same as x to the 1/2 power dx, in which case, if we still follow this power rule, we would get 3/2 by adding 1 to the exponent. We then multiply by the reciprocal, which would be 2/3 plus c. Suppose we have a radical in the denominator like this, 1 over radical dx. This is going to be the same as the integral of x to the -1/2 power, and so when we accomplish this, we first add 1 to the exponent, so we get x to the 1/2 power. We then multiply by the reciprocal of that, which would be 2 over 1 plus c, and this simplifies to 2x to the 1/2 power plus c. Simplifying these, this first one, 2/3 x to the 3/2 power, we can imagine this as 2/3 with the square root of x to the 3rd power plus c, where the radical only pertains to the x cubed. Likewise, for this 2 times x to the 1/2 power, this would be 2 radical x plus c. Now, there's actually a limitation to this integral equation, such that the integral of a to the x to the n power dx, this only works when n does not equal -1, in which case we would have the integral of a to the x dx. And we know this to be the integral a, which is moved outside 1 over x dx. This would always be equal to a times the natural log of x plus c. So let's look at an example like this. Suppose we want to take 3 over x, the integral of that. This would be equal to 3 times the natural log of x plus c. If we want to have the integral of 2 over 5x dx, we see that the 2/5 is actually a coefficient that's multiplied out this way, 2/5 times 1 over x integral dx. And so the 2/5 will come out of the integral so that we get 2 over 5 times the integral of 1 over x dx, in which case this would be 2/5 natural log of x plus c. Related to these natural log functions, we also have the integral of exponential functions. Suppose we have e to the ax dx. As the coefficient in front of the x is going to be a, this would always be equal to 1 over a e to the ax plus c. So for example, if we have the integral of 5x dx, the answer to this would be 1/5 e to the 5x plus c. if we have, for example, e to the negative 2x integral dx, this would actually be equal to negative 1/2 e to the negative 2x plus c. Related to exponential functions, what happens if you were to raise a constant to the x power? So let's suppose that we have the integral of a constant 3 to the x power dx. This would actually be equal to 1 over the natural log of 3 times 3 to the x plus c. For example, if we have the integral of 2 to the x power dx, this would be equal to 1 over the natural log of 2 times 2 to the x plus c. If you have the integral of 3 to the 2x dx, now we know that whenever we raise an exponent to an exponent, this is really 3 squared raised to the x power. So we could imagine this as the integral of 9 to the x power dx. So using the same formula, we would get 1 over the natural log of 9 times 9 to the x plus c. Next we have trig. And so in my previous example, we learned if we were to imagine this as a xy coordinate as well as a unit circle, we have the positive x and y axes on the right and the top respectively. We can imagine the x as the cosine and we can imagine the y as the sine. And therefore the opposite directions of these would be the negative sine direction and the negative cosine direction. As time moves forward in clockwise direction, which is derivatives, we can imagine the counterclockwise, so counterclockwise direction as integrals. So let's look at some of these examples. So first we would have the integral of cosine of x dx is going to be sine of x plus c. The integral of sine of x dx is going to be negative cosine of x plus c. The integral of negative cosine of x dx is going to be negative sine of x plus c. The integral of negative sine of x dx will be equal to positive cosine of x plus c. We know integral of secant squared x dx will be equal to tangent of x plus c. We have the negative integral of cosecant squared of x dx will be equal to cotangent of x plus c. Two more, we have the integral of secant of x tangent of x dx will be equal to secant of x plus c. And the negative integral of cosecant of x cotangent of x dx is equal to cosecant of x plus c. Now for those inverse functions, the main two that we have is going to be the integral of du over the square root of a squared minus u squared, in which this will be equal to the arc sine of u over a plus c. And we have the integral of du of a squared plus u squared. This will be slightly different. This will be 1 over a arc tangent of u over a plus c. So those are the most basic integrals that we expect for topic 6.8, finding the antiderivatives. We move on to topic 6.9, which is integration using substitution. Now for these sort of substitutions, it's the idea of doing a u substitution for two types of functions. So you could either use a u substitution to set it equal to some function like mx plus b, in which x is to the first power. So those are going to be type 1 u substitutions. Type 2 u substitutions would be if u is equal to f of x, such that du is equal to f prime of x dx exists, which will make the problem much easier to solve. So let's start off with type 1 functions. And so we're going to start from the beginning. Recall that we had this type, the integral of x to the n power plus c, in which we had some sort of power. This was equal to a times 1 over n plus 1 times x to the n plus 1 power plus c, where we had the integral of x cubed dx. This was equal to 1/4 x to the 4th power plus c. But what if instead we have x plus 1 raised to the 3rd power and we wish to take the integral of this? Now, some of you guys are going to actually multiply x plus 1 times x plus 1 times x plus 1, which would just be x squared plus 2x plus 1 times x plus 1. Hence, x plus 1 is raised to the 3rd power dx, in which case this would be x cubed plus 3x squared plus 3x plus 1 dx. But do note that we have not yet taken the integral. All we've done is we foiled this. And so when we take the integral, we get 1/4 x to the 4th power plus x to the 3rd power plus 3 over 2x squared plus x plus c as the answer. But instead, we're going to use a very intelligent substitution type 1 substitution in which we set u is equal to x plus 1. Now, earlier in the notes, we found that u was equal to some sort of linear relationship, and this is very important because x is to the first power, in which du is just going to equal dx. Dx being over here. So in this case, we have u that's raised to the third power multiplied by du, and this is a very easy integral to solve. We know how to do x cubed, which is going to be 1/4, so all we've really done was solve for this as the integral of u to the third power is going to be 1/4 u to the fourth power plus c. But we do know what u is equal to. U is equal to x plus 1, so this is going to be 1/4 x plus 1 to the fourth power plus c. Now, for some of you guys, actually solve for this foiling, and when I solve for x plus 1 to the fourth power, I get x to the fourth power plus 4x cubed plus 6x squared plus 4x plus 1 plus c. In which case, when I distribute this 1/4, what you're going to see is that this will equal 1/4 x to the fourth plus x cubed plus 3/2 x squared plus x plus 1/4 plus c. And what I want you to notice is that these terms are very similar except for this last part, 1/4 plus c. Now, this constant is some sort of constant. Let's call this c1. This constant is 1/4 plus c, but let's call this c2. What you'll notice is that these two are roughly the same because we're creating an arbitrary constant. Whereas if you have an arbitrary constant c2 that's added to 1/4, for example, that's just going to provide another arbitrary constant. So we see that this sort of integration by substitution works for type 1 cases. For a type 2 case, let's suppose that we have the integral 3x squared plus 4. This is raised to the second power. We would take the integral of this dx. And we also have what is a 6x on the outside. Now, regular people would look at this and say, well, I have this square. Let's actually FOIL this. This is going to be 6x, 3x squared plus 4 times 3x squared plus 4. And if you were to FOIL this, this would look like 9x to the fourth power plus 24x squared plus 16, which still multiplies to the 6x, in which case when we then distribute this, we get 54x to the fifth power plus 144x to the third power plus 96x, which we've only distributed, have not taken the integral yet, dx. And by integrating this, we get the following. We get 9x to the sixth power plus 36x to the fourth power plus 48x to the second power plus c. Rather, what we should do instead, we should do a u substitution. This is going to be type 2. So type 2, we have to first find a function that we set equal to f of x, and that'll be u is equal to 3x squared plus 4. And the reason why I do this is because if we were to then do du, we see that du is going to be equal to 6x dx, which happens to be the same power as this 6x term. So that the 6x and the dx gets all replaced with du, so we have an integral where it's just going to be u to the second power du. We know how to do this integral. This is just going to be 1/3 u to the third power plus c, in which we would then replace the u with this 3x squared plus 4 to the third power plus c. And now let's actually multiply this out. Now, if you guys know Pascal's triangle, our coefficient should be 1, 3, 3, 1, where the distribution of this would be 1/3 times. We have 3x squared raised to the third power, 4 raised to the 0 power, plus 3 times 3x squared raised to the second power, 4 to the first power, plus 3 times 3x squared to the first power, 4 to the second power. And we have essentially 3x squared to the 0 power, plus 4 to the third power, which is then all going to be multiplied by this 1/3. So the first one that we get is going to be what appears to be 27x to the sixth power. Then we have what appears to be 27x to the fourth power times 4, and I believe 27 times 4. We're going to eventually divide this by 3. So let me actually write divided by 3 to show that we're also distributing that 1/3 at the same time. The second term appears to be 144x squared all over 3, and then finally we have what appears to be 4 times 4, which is going to be 64, all divided by 3, and we still have this plus c. Now, similarly to what we had before, this combination of a constant with an arbitrary constant c can form another arbitrary constant. When we simplify 27x to the 6th divided by 3, that's going to be 9x to the 6th power. When you multiply the 27 by the 4 and then divide by the 3, we could actually divide those two things first. So we get 9 times 4. That also gives us 36x to the 4th. 144 divided by 3, that's going to give us what I believe is 48x squared. And plus, I'll just put c2, and we see that these two terms are going to be the same. So those are the two types of u substitution methods.